So hello everyone, I'm Wenke. In my talk, I'm going to talk about distributed programming in OCaml based on the actor model. This work is did for my master internship. So I'm under the supervision of Ludovic and Gabriel. So the objective of this work is to allow distributed programming in OCaml based on the actor model. So in this talk, first I'm going to talk about what is the actor model and the library to manipulate with actors, and then is the implementation we need to support the distributed programming, and then I will talk about the runtime architecture of this implementation and the compile time implementation. So what is the actor model? So in the actor model is a model for concurrent programming. In this model, we are programming with an entity called actors. Each actor has a private state, and it has some asynchronous messages, and they are often implemented by features. You can see here in the graph that we have two actors that are sending each other messages. And when one actor receives messages, it will trigger a function to be executed by a scheduler inside of it. The scheduler will schedule this method to be executed asynchronously, and this method will access to the private data, will access to the private data. And each actor is bounded to one particular logical thread. So in this model, we have the advantage of data race freedom. And how are we gonna define actors in our code? So here in a pastel code, we first declare the name of this kind of actors. Here is the counter. And then we specify in the code that we have two private states, which are X and Y. And then we will specify what kind of messages this counter can receive. And in our case, it's the increase and the decrease. And inside of each messages, we will implement we will write the implementation. So in practice, how we're gonna write them, particularly in OCaml. So here is the code that using the OCaml object feature to define actors. So here is the same that we define a counter actor, which we using the object attribute for the private state, here the X and Y. And then we will use the object method to define their messages. And here is also the increase and the decrease. But here, as I said, that the method will be executed asynchronously. But here we only write synchronized code. So this here at the beginning, right after the class, we have a PBX extension point that will transform all the method of this object to make them return future. And when this method gets to call, it will be put into a scheduler. So after to create an actor, what we need to do is to use the new keyword to create that actor with the initial argument. And then we will able to send messages to actors using the object method. And here is a program that written by that based on actor model. So we have many actors sending each other messages. So here it will be the object method calling to each other. And this call go through memories. And to extend this kind of stuff to distributed programming, what we need to do is only to put box around actors. Because in the actor models, each actor do not have shared memory access between actors. So it means that the actors can be located in different physical memory. Also, the method call between actors are asynchronous. So it means that the call can go through networks. So this allows programmer to transparently programming in distributed system. And to implement, to support such kind of stuff, we need to implement a runtime system to support all the operation I said before through networks. And then it turns out that this runtime system needs some meta information from the programmer defined code. So we have a PBX extension that will be executed statically to analyze the programmer write code and to generate the metadata for the runtime system. And here is the implementation. Here is all the implementation we need for this distributed system. The first, we need to support creating an actor in a remote node, and then call method of a remote actor and get the future of that ongoing computation. And then later we will be able to query the result of that computation based on that future object. And then in the distributed system, we'll be able to share actors and futures through the system. And here I'm going to talk about the point 2, 3, and 4, because we don't have that much of time. So here is an example of how to remotely call actors in the distributed system. And at the line 2, we will, after creating an actor, which is a counter, and at line 3, we will call its method by the object method. And later, we decide to inquiry the result of that call. So to implement this, when the method get called, when we execute that method, after creating the counter, we will be able to get an instance identifier for that counter. And we will generate a call ID for this remote call. And then we will send all the necessary information of this call through network, including the method name and also the argument that we apply for this call. And when the node 2 receives all the information, he will be able to identify the original actor that was instantiated before here. So he will execute the code. And then when the computation finish, he will actively send results back to the node 1. So that's why you can see here they are using two different connections for communication. And we're back to node 1. When after sending the request at node 1, the node 1 will generate a local future entity represent that remote call. And this local future, the state is based on the result of the node 2. If the result has been sent back from node 2, the future will be ready. Otherwise, we will wait for it to synchronize, or we will use the cooperative scheduling. And then is another case that how we're going to share actors in the distributed system. Here is an example that we have two actors. Another one is the downloader, which requires a counter at the beginning, and when he downloads from some stuff, he will increase that counter. So you can see here in the line 9 that when we create this downloader, we need a counter. We need a counter. So how we gonna? You can see here that these two actors are in different nodes. So how we gonna serialize the counter to the node 2? So it turns out that we cannot copy all the binary data of that counter through network and reconstruct them on the other side. Because first, it's not possible practically, because actor has a scheduler and it has some ongoing computation, so it has some many continuation and closure. It is impossible for us to copy all of them. And secondly, based on the actor model semantic, we should not copy them. One actor in the model representing one execution thread with ongoing computation. So when we share actors, what we are actually sharing is the reference to that actors. So it means that we will apply special serialization policy for actor objects. So you can see here at node 1, after creating two actors and passing the first one to the constructor of the downloader, we will serialize the first counter to a counter descriptor, and we will send them back. We will send them through the network to the node 2. And then at the node 2, he will be able to reconstruct a mock counter based on this descriptor. What is a mock counter? Mock counter is a kind of mock actor. A mock actor has the same method as its original actor, but all the implementation of their method is just sending request to the original actor. So after we reconstruct a mock actor at node 2, the subsequent sequence will be the same. We're just creating a downloader and do the stuff. So, and about the future, it's the same, that we will apply special serialization for future objects because we cannot copy them. And that is the architecture for this runtime system. As you can see before that in the distributed system, each actor has some I/O operation to other node. So we decided to centralize all the I/O operation to one special thread, which we call the proxy thread. This will improve the efficiency of the node. And this proxy thread will use the concurrent I/O to manage all the network operation between nodes. So actually, the request between nodes are the request between the proxy thread of that node. And also, the proxy thread will also serve to manage the state of each node. It has many tables, like what are the actors in that node, and what are the call we have sent before. And the communication between actors and the proxy thread is through memory and through a queue. So that is the compile time implementation. For example, when we create an actor remotely, for example, the programmer at node 1 want to create an actor at node 2. When we actually create that actor at node 2, we need to find out the constructor of that actor. But in OCaml, we cannot write code like a class and get a constructor to reflecting the constructor that the programmer defined before. So we need a runtime reflection to get that constructor. And it is same for the actor method, that when we remotely call a method, even we know the name of that method, we cannot using that literal value to getting that to execute that method. So we also need to build a reflection mechanism for this kind of stuff. And also, as I said before, that mock actors and the mock class has the same method of the original actors, but with different implementation. So we, at the compile time, we will analyze the original actors and generate the mock actors and the mock class. So the general step to implement this is that by the person actor extension point, we will able to inspect the structure of the class, and then we will insert the metadata we need. And then eventually we will insert some code at the beginning to initialize the runtime environment. All this is done by the OCaml PPX. And in summary, we have delivered a library that is based on actor model for distributed programming. It allows create actors remotely, call actor method remotely, and query its results. And also in this distributed system, we can share actors and futures. And this library abstract away all the network details. But unfortunately, there are something we did not accomplish. That is, this library is not fully transparent for distributed programming. The programmer must explicitly mark the data type. That is why, as I said before, we apply special serialization policy for actors and futures. But unfortunately, we cannot distinguish the variable at runtime if it's an actor or a future or a value. So we need a programmer to explicitly mark them for us, and we can apply proper serialization. And this library is available in this website, and the example I shared before is available at the examples folder. And that is all of my talk. Thanks for listening.
Thank you. I think we have some questions.
Yeah, let's say that like I send an actor an RPC and like a cosmic ray like flips a bit in its memory and it crashes, and so like that RPC is going to return an error. Like, does this framework have any built-in error handling mechanisms or error recovery mechanisms? Framework have any built-in error handling mechanisms or error recovery mechanisms?
Sorry, you did not turn on your micro, so I do not listen your questions.
Can you hear me?
I saw that in the live stream. Sorry, you did not turn on your micro, so I do not listen your questions.
Can you hear me?
Sorry?
Do you have any error handling mechanisms or error recovery?
The Discord account in the session this micro is closed.
Sorry, Wenke. I mean, the audio is not working very well, so I'm going to answer. No. More seriously than that, we try the minimum, but implementing error recovery in a distributed system is a big task, and so we didn't take the time to do that.
There's another actor framework called Riot. How does this work compare to that? And have you thought about collaborating so that we can have one implementation rather than multiple?
Yeah. So the objective of those two libraries are pretty different. So Riot implements the runtime actor, so Erlang style, I would say, and this. So we worked a lot for the distributed part, but the basic idea was to have the programming style in Scala-like actors. And so that, yeah, in practice, those are two very different programming style. I would hope that eventually everything will be based on Picos, and then we can share everything. Yes, eventually I want to do that, yes.
And yeah, and I have, I guess, a beginner question about actors and the actor model. Could you give like some examples of the kind of applications it's good for or convenient? Like if I want to write a distributed application, what would be a good fit for that?
So basically, actors are pretty good when you need task-based parallelism with internal state. That's the main thing it is good for. So things that are a little bit big, but that can be shared. So yeah, that's the main idea. So you can think of, for example, actors that will delegate some work to sub-workers. Yeah, so these kind of things, depending on your on how efficient we can make it. You can think of coarse grain computations. So yeah.
Okay, thanks.